Okay, let me continue from yesterday. This is lecture 6. I continue elementary matrices and inverse. Well, I did something yesterday, in the last lecture, which was wrong. I'm not sure if anybody caught me. So I applied this row operation to in k times row I plus row j, and I made a big mistake. So what do you think the result is? But definitely nothing changes except j, because the end result goes here, row j. So nothing changes here up to even I doesn't change. Goes down to the jth. What happens here? Well, let me just go down on this. Well, what happens here? Well, when I multiply row I by a constant k and add, this is added to a 0 here. Where is this 0? This 0 is in the ith column. This is the jth column. See, I, j, j. These are the ones are at intersection of ith column and ith row. Jth column, jth row, or jth column, jth row. So this k is multiplied by this added to this. So the jth row has zeros except at position I and position j. So it will be 0. So let's say this is position I in column wise, and this is position j column. So let's see, let's move on. Let's put this one here. Okay. Let's put one here. Okay, so this multiplied by k added to 0 will give me k. This doesn't change. So I will get 0, 0, 0, 0. So the jth row has, say, k in this position. But I can, let's apply it to, say, I5. I can explicitly 0. So this is I5, and let's apply this to I5. So let's take row 2, I is 2, and let's say j is 4. Okay. So let's do this. K times row 2, row 4, row 4. Row 2, row 2, row 4, row 4. Okay, so when I apply this, well, let's do it right here. So when I apply this, this happens. This is multiplied by k. Just I will get a k here, and k is added to this. So I will get k here. So this is the result. Now what do you think the inverse of this is? The inverse is just minus k times this. So the inverse of this is minus k row 2 plus row 4 goes to row 4. So if I do that, I'm multiplying this by minus k, adding to this. This is 0 then, nothing else happens. So if I apply this, I will get I5 back. Now let's look at something else. What if I multiply this by a matrix which by In after applying this? So if I apply 2, 3, 5, minus k. But I'm trying to make a point here. So this matrix is, after applying this, I will get this matrix to I5, and I will get this after applying this row operation to I5 again. So these two, I said if I do this operation, this row operation, apply this row operation to this matrix, I will get In. Now I'm trying to say that if I multiply this by this matrix, I will get In again. So either applying this to this matrix or multiplying this by this matrix, I will get In, I5 in this case. So let's do this. Let's see what happens. And let's write the result here. I have some space. So this times this, 1. I will get, so you see this one multiplied by anything else will give me 0, right? Because this multiplied by 0, everything else 0. This multiplied by 0, 0. This one multiplied by 0 is 0 and so on. So this one only gives me that row. Now this one similar to that, it will give me this. You can try it and see that this happens. And this one also gives me 0, 0, 1, 0, 0. Now let's see what happens here. This is k times 1, 0 times 0. So let me put that right here. So this is multiplied by this. So let me write it explicitly: 0k, 0, 1, 0, and this is multiplied by 0, 1, 0, negative k, 0. 0, 1, 0, no, yeah, that's right. Okay, so this multiplied by this, that will give me, but the first one is 0, the first one is definitely 0, so I want to see what happens here. So this times this will give me 0, because there's just 1 here, 0 times 1 is 0. Okay, so it's 0 plus k, 0 times 0, 0, 1 times minus k, plus 0. Wow, 0. So this one is also 0. So after applying this, and multiplying this to this, I will get 0. And the rest is the same, so it says 0, 0, 0, 0, 1. So it seems that this is the inverse of this. This matrix is the inverse of this. Okay. Now let's look at something else. Since this operation is important, let me do this operation. So this operation is more important than the other operation. So let's see. So after applying this to I5, that was I5, I will get this. So let's call it E. This E is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, no, sorry. 0, then I have 0, k, 0, 0, 0, and 0, oh, 0, 0, 0, 1. Okay? So let me apply this to a 5 by 5 matrix. And I will use, I am not going to use numbers, I will use AIJs. And there's a reason I use AIJ. Let me see if I can find another color. The blue one, G. Blue. Look at that. So let's apply this to a let's see. This one times this will give me a 1, 1, a 1, 2, a 1, 2. So this row multiplied by the columns will give me the first row of the result. So I think I have enough space here too. So the first row doesn't change. Nothing happens to the first row. How about the second? This multiplied by each one of them gives me the second row here. So this 1 is multiplied by each one of them and will give me just that. The rest are 0. So just multiply and you will see for yourself. So the second row doesn't change. The third row doesn't change. Now what happens to the fourth? So everything is in fact happening to the fourth row. You see, I'm just changing the row number 4, nothing else. Okay, now multiplying this by this, just look, 0 times this is 0. K times this is K A to 1. So let me, let's write it here again, like the other one. So I'm multiplying this, make this vector 0, K, 0, 1, 0 by this A, 1, 2, A, 2, 2, A, 3, 2, A, 4, 2, A, 5, 2. So this is what happens here, right? Oh, gee. First I should multiply this by the first one. So that is 1, 1, 1. So each all of them are 1. 1, 2. 1, 1, 1, 1. Right. So this time this will be this entry here. Okay, so let's do it. 0 times A, 1, 1, 0. K times A to 1, A to 1. Plus 0, plus A 4, 1, plus 0. So it is K, A 2, 1, plus A 4, 1. So this term here, this one here is K, A 2, 1, plus A 4, 1. Do it here, you will get K, A 2, 2, plus A 4, 2. Up to the last one, K, A 2, 5, plus A 4, 5. The last row remains, nothing happens, A 5, 1 up to A 5, 5. So what happens to the fourth row? This is the fourth row. So after multiplying this from the left by this matrix, this elementary matrix multiplied by a generic matrix 5 by 5. This elementary matrix did this. Nothing happened except in the fourth row, and the fourth row seems to, it has changed in this way. This row is multiplied by k added to this. This row is multiplied by k and added to this. So it seems that multiplying this matrix by this elementary matrix has the same effect as applying this row operation to this matrix. So let me say it again. Pre-multiplying this generic matrix by this elementary matrix has the same effect as applying this row operation to this generic matrix. So row operations can be performed by matrix multiplication, right? So, well, this in fact has a consequence when you're writing a computer program. So you can write a program that can generate elementary matrices, and then another program, well, matrix multiplication is always there, but another one, say, for matrix multiplication, and then when you want to do a row operation, just multiply from the left one of those elementary matrices by your matrix, and then it has the same effect as that row operation. Anyway, so now we will see why I'm saying this, because I have a point here. So let me erase this thing. So I would say that, let me see how I can phrase it. Say applying a row operation on a matrix A, say, is like multiplying but I will check the right too. So multiplying from left matrix A by the corresponding elementary matrix. So I can say this. A, say, apply row operation, say row operation I to IN, B, say, to get, say E, say I. Now this EI comes from this, to get EI. EI times A is like, how should I say that? EI times A has a, is EI times A has the same, gives me a matrix that can be obtained by applying operation I to A. So either pre-multiplying A by EI or applying operation I on A, they have the same effect on A. So they will give me is something. So I can say that EI times A is the same as applying I to A. Okay? Okay, so now what are we doing in fact? When I'm applying a row operation to a matrix which is equivalent to pre-multiplying the matrix by some EI, then I'm going towards what? I'm going towards RREF of A, right? So row operations, don't forget what we are doing. Row operations are to turn the matrix into its RREF, reduced row echelon form. So I apply some row operation, say well, let's go from left to right, because if it's multiplied like this, so let me give enough space. E1, then I apply another one, E2, then I apply another one, E3, up to E, say, K, something. And this becomes RREF of A. Okay? So I apply or pre-multiply A by some elementary matrices, say E1 into E3. It depends how many I need. And then I will get RREFA. What if A is invertible? Remember the theorem? If A is invertible, then RREF of A equals IN. Right? If A is invertible, let me remember this thing. This is important. Recall, if A is invertible, then RREF of A equals IN. And I'm assuming that A is n by n. Remember, we started with n by n when we are trying to find inverse. So let's assume that. So let us assume that A is invertible. Okay. Then what happens? If A is invertible, I will get this EK, E3, E2, E1A will be IN, right? If it's invertible, its RREF is in form IN. So that theorem, in fact, was for this purpose. Now, I'm assuming that A is invertible, which means A inverse exists. So let's write IE, A inverse exists. I don't know what it is, but I know it exists. If I'm assuming that it's invertible, then A inverse exists. So let's multiply from right, sorry. Let's multiply from right by A inverse. This is crucial here. If you understand this, you will understand the whole thing. So if I do this, this happens. So let me write it here in front. So I have EK, E1, A inverse, IN, A inverse. Okay? So I have this. A inverse is IN. So EK E1, IN, and I have a reason to write IN here. Because you might say, okay, IN times anything doesn't make any difference, so I can just ignore this IN. No, there is a reason I wrote this. Is A inverse. Okay, so this is what I got here. So if A is invertible and EK up to E1A gives me IN, then look at this. EK, E1, IN is A inverse. EK up to E1 times IN is A inverse. So, if I know the EIs, those elementary matrices, if I multiply them, well, this doesn't change anything. So if I multiply them, in fact, A inverse is the product of these. A inverse is the product of these. But there's a reason I have written that IN over there. So you can say, okay, yeah, so this also means that I have found A inverse. So if I know all these things, then it is in fact a product of the EIs. A inverse is product of these EIs. That's correct. But I need this one for an algorithm. I need this. Okay. Let's go back to this. EI times A is like applying operation I to A. E1 times IN is like applying operation 1 to N. E2 times the rest is like applying that operation to the result, and so on. So if I start with IN and apply all the operations that change A1 into IN, so if I apply all those operations to IN, I will get A inverse. It's not multiplying. If I do the same operations on IN, I will get A inverse. Now, there is a practical way of doing this. And that's maybe what you have seen in college algebra. So if I have A, write A here, and write IN here. Okay? On the right side. Then apply the EIs to A. Let me give it some space. So apply all the EIs. So E1, E2, EK. And do the same thing here. What happens? What do I get? If A is invertible, I will get IN here, and I will get A inverse here. Okay? Right? So this comes from this fact, and this comes from this fact. Right? This is because of this, and this is because of this. I mean, not this side. This side is in fact this equals this, and this equals this, right? Okay, so that's the algorithm. Write them side by side and apply the row operations that turn this side into IN, and what you have on the right side is A inverse. Yeah, apply all the operations to IN. Now, there's one thing. Well, you might say, so what if I do not get IN on this side? Well, that's good, in fact. No, I'm not saying that good, that's good. But that means A is not invertible. So if you don't get IN here, forget about it. That matrix is not invertible. Finished. So we'll try an example here. So let me erase everything and apply this algorithm. nice example of something irrelevant. There's a nice example. Yeah. Wow, it takes. Oh, okay. So this is the matrix. The matrix is 1, 2, 3, and 2, 5, 3, and 1, 0, 8. So this is A, right? And 1, 0, 0, 0, 1, 0, 0, 0, 1. And this is I and C. Okay, so what is the first row operation? I should get rid of this and this. Multiply this by -2 and add to this. So it is -2 times row 1 plus row 2 goes to row 2. Okay, so let's do it. So -2 -4 -6. 2, 5, 3. So I have 0, 1, and -3. 0, 1, -3. So let's erase the second row. Now the second row is just 0, 1, -3. 0, 1, -3. What happens here? I said apply the same operation to this. So I have -2 row 1, I have -2, 0, 0, and 0, 1, 0. So when I apply, I will get -2 here, 1 here, 0 here. So the second row will be this: -2, 1, 0. Okay. Well, another operation is getting rid of this, so it's -1 times row 1 plus row 3 goes to row 3. So let me do it here on scratch paper. So I have -1, -2, -3, 1, 0, 8. So that's 0, -2, and 5. So I have 0, -2, 5. 0, -2, and 5. Now what happens here? I have -1, 0, 0, 0, 0, 1. That's the third row. -1, 0, 1. So the third row will be -1, 0. Okay. So up to this point, I eliminated these two. Let's go to this one. I should use this to eliminate this. Well, that's very simple. I multiply this by 2 and add to this. 2 times row 2 plus row 3 goes to row 3. So let's see what happens. So this multiplied by 2, I will get 2 here, -6 here, and I have a -2 here and a 5 here. I will get 0 here, -1 here. So 0 -1. Let me double check. 2 -6 -2, 5, and that is 2, 0 -1. 0 -1. Let's do it here. So apply minus. What was that? -2, not -2. 2 times this will give me -4, 0, 0, and I have -1, 0, 1. So I will get -5, 0, 1. -5, 0. Oh, sorry, that is 2 here, right? I'll multiply this by 2. Let me see. So there's a 2 here, right? So minus 5, 2. So there's a 2 here, right? Go back to 1, 2. Minus 5, 2. Okay. Well, 1, 1, this is negative 1. So let's multiply the third row by minus 1. Minus 1 times row 3 goes to row 3. And this just changes the sign. So this changes the sign here. Minus 2, minus 1. Okay, now I should use this to get rid of this and this. You see, I need RREF. So I have to continue. So to get rid of this, I have 3 row 3 plus row 2 goes to row 2. Okay? Let's see what happens here. But this one is easy because these are zeros. 3 times 0, 0, nothing happens here. So the only thing happens is this thing. So that becomes 0. But what happens here? This is important. That one is easy. We know that this makes this 0. So I have 3 times row 3, that is a 15 and minus 6 and minus 3, right? And then add it to minus 2, 1, 0, I will get 13 here, and minus 7 here, and minus 3. No, minus 5, sorry. So, that is the second row, 13 minus 5 minus 3. Right, let me double check. 13 minus 5 minus 3, okay. Another one is, I should get rid of this. So it is, in fact, minus 3 times row 3 plus row 1 goes to row 1. That eliminates this and this becomes 0. What happens here? So minus 3 times this is minus 15, minus 3 times this is 6 and 3. Getting, and add it to this 1, 0, 0. So I have minus 14, 6, and 3. So minus 14, 6, and 3. Okay. At last, I should get rid of this. And I have to use the second row to get rid of this. Now, you see the RREF, I didn't do a complete RREF for you. So RREF starts with this, you eliminate this and this. Then you go here, eliminate this if you have anything down. So you go one by one and eliminate. Then you go up. When you go up, you start with this, eliminate this, then this, eliminate this, then this, eliminate this, okay? So that's how you do RREF. You first go down to the right, then up to the left. Okay, then at last I should get rid of this 2, so it is minus 2 times row 2 plus row 1 goes to row 1. So I know that this becomes 0. This one is important to do correctly. Minus 2 times this is a minus 26. Minus times that's 10, minus 2, that's 6, right? 26, 10, 6. And add it to this, minus 14, 6, and 3. So I guess I get minus 40, 16, and 9. So I have minus 40, 16, and okay, I'm done. I am done. Now what do I have here? This change into I3. It also means that A is invertible. And this change into A inverse. So A inverse is this matrix. So that is how you find inverse of a matrix, the algorithm. And as I said, you might have seen this in college algebra. It's the same thing, except maybe you didn't know why this happens. So I'm not saying this is exactly the proof, but anyway, I showed you why this happens, why applying the same row operations to In will give me A inverse. Okay. So let me erase this, and I still have some time, so let me start the other topic. So this is in fact 1.6, but I'm continuing on matrices, linear systems, and invertible matrices, more on inverse and linear systems. So this is in fact an important theorem which I mentioned before in 161. A system of linear equations has either a no solution, which we sometimes we say inconsistent, B, just one solution, and C, infinitely many solutions, still consistent. So, let me let's go deeper into, delve deeper into this and see what really means. Especially you might wonder what happened from 1 to infinite. There's no system that has 2. Well, let's look at that. If a system has 2 solutions, what happens? Let me erase this. So this is okay. So you did get no solution. If there's no solution, finished. If it's one solution, it's one solution. Done. It's between 1 and infinite which needs some discussion. What happens? What if I have 2? So let's look at this situation that the system has 2 solutions. So let us assume that, remember a system, I can write it as this, ax equals b, right? As two solutions, x1 and x2. Let's see what happens. So I have a x1 equals b and a x2 equals b. Let x be, say, x1 plus some constant x2. Okay? x1 plus some constant times x2. And let's assume x1 and x2 are different, say. So, what happens? Let's apply a to x and see what happens. So, it is a times x1 plus k x2, and this is ax1 plus, you know that the k, this is a matrix multiplication. So these vectors are column vectors, so you can multiply, and this is just a constant. So the constant comes out ax2. Well, this is b, and this is kb, and this is like k plus 1b. Well, this doesn't work. This doesn't work. But what if I do this? What if I say, okay, instead of writing b here, let's write 0. So in fact, these are not two solutions. One of them is the solution to ax equals b. The other one is solution to ax equals 0, right? So x1 is solution to this. x2 is solution to this. Okay? Well, you might say, does this have a solution equals 0? The answer is yes, it does have a solution. This system is always consistent. Why? Because 0 x2 equal to 0 is a solution. And if I have a solution, it is consistent. So this system is consistent. There is at least one solution, that is 0. So if I do the same thing, then this one is b and this one is k times 0, and I will get b back. I will get b back. So it seems that this x, which is the sum of a solution to b, this equation, and some constant times solution to this one, is another solution. So if I add to x1 any solution here times the constant, that vector is another solution. That vector is another solution. So let's say it again. I find a solution to this. Suppose I have one solution. And suppose, well, this is not two solutions, but let me erase this. This is not two solutions. So I have one solution here, so it means it is consistent. Then I find one solution to this equation, call it x2, then I add x1 to some constant times x2, and I show that this new vector is another solution. This k is arbitrary, so this k can be any real number. Therefore, this can give me infinitely many solutions. By changing the k, I have infinitely many solutions. But you can ask this question, what if this has only one solution, which is 0? If this has more than one solution, just another one, not 0, just another one. And I write it here, then I will get infinitely many solutions. So it comes down to this one, and asking this question, does this one have more than one solution, or in what condition it has more than one? We know it has at least one, so it is always consistent. The system which has 0 on the other side has at least 1 0, so it is always consistent. So now I will